Okay. Let me know if there's any trouble seeing the PowerPoint. Um, but anyway, welcome everyone to week 2 of our Artificial Intelligence for Medical Students workshop. Today, we're going to talk a lot about how to look at data and some really initial artificial intelligence methods, which we'll have a programming example for. This is one of my favorite quotes, which Abraham Lincoln says, "Don't believe everything you see on the internet." And that theme is going to come up a lot when you see examples of data being misused and misinterpreted. So, try to advance the slide. So agenda today, we're going to go over some biostat prerequisites from last week, and then we're going to really go over how to look at data, problems with data, how to prepare it for machine learning, how to generalize it. And if we have time, we'll talk about supervised, unsupervised learning, and logistic regression, which is one method of machine learning. Essentially, we're going to talk about how to look at data and prepare it for machine learning. Now, this is a motivating example I always like to share. So each one of these data sets has the exact same mean, standard deviation, correlation coefficient, right? And this just shows you how limiting relying on really traditional linear statistics can be. If you just do a p-value analysis or t-test or a Pearson correlation ratio or odds ratio, each one of these data sets will give you the same conclusion, but they're very evidently very different data sets and represent something very different. So last week we talked about there's a difference between descriptive statistics and inferential statistics. Descriptive is just metrics like mean, standard deviation, spread, where it's just a characteristic of the data, but you're not making any conclusion. Inferential statistics, you usually go one step further. Some people, they classify odds ratios, p-values as some inference, which is sort of true. You're making some sort of conclusion, like p-value, you're saying that these two data sets are significantly different. But there's also one step further, which we would like to go in machine learning, which is we want to be predictive. So we don't just want to say a p-value. We want to, for instance, use that p-value and say that we can use this p-value as a threshold or this odds ratio as a threshold to predict the outcome of a disease occurring. So this is an example of using odds ratios to interpret different treatment options for group A strep. So here they're reporting the odds ratio, and you notice that, okay, well, clindamycin with no IVIG has a lower odds ratio, right? So what does this mean, right? How do you know what threshold of odds ratio is good enough and what threshold of odds ratio say, okay, this treatment regimen is preferred in this case, right? So this is a limitation of using inferential statistics that aren't predictive. They give you some insight, but it's up to the physician, up to you to use that odds ratio somehow. And this goes back to the classic way of, just wait for these slides to advance. Classic way of developing sort of scoring system and using data in medicine, where you do some descriptive or inferential analysis of retrospective chart data. There are a million projects going on doing this. You make some scoring system or some flow chart using your highest odds ratios variables. And then you use that flow chart, and then people do different review studies on your flow chart to see what sensitivity and specificity you have. This is sort of the old method of doing it. And one really common one that a lot of first years encounter is the center score for pharyngitis, right? You get a point if you have fever, you get a point if you're absence of cough, and then your test probability increases of having, pharyngitis potentially due to group A strep. And you see that these post-test probabilities, they're not great, right? 55.7%. I mean, it's better than nothing. It's still useful in clinical practice, and this is still used every day, and we still learn this in school. But you see that it's not like 80 to 90% that you expect from machine learning studies. And one telltale sign is that, okay, well, these points, they're whole numbers, right? When in nature do relationships result in whole numbers? Usually not. This is usually made for convenience so that it's easy to use. Now, there's still an argument that it's still very useful clinically, but it's not as accurate as it can be, which is what we try to improve on with machine learning. So just hammer this thing, odds ratios and p-values, they're not accuracies. They tell you a characteristic of the data set, which can be useful, but it will not give you the highest accuracy measurement if you just manually interpret them. So, and we know the medical world is slow to adapt with new methods, particularly with machine learning methods. So this is a study that looks at, you can read it in your spare time, how odds ratios is not the best gauge to develop diagnostic or prognostic tools. It usually gives around 60% accuracy, which is okay for screening, right? If we just want to catch people at any risk, we don't want to miss any positives, we can use odds ratio, but it's not great and it can be improved. So this is the machine learning paradigm. This is the crux of machine learning. We take some input variables, so exactly the same as a traditional method. We make a model that analyzes the variables. So this model could be a logistic regression model, a neural network, but essentially it's a parameterized model that will update itself so that the output of the model is a prediction. So it might compute an odds ratio, but it'll automatically compute a threshold for that odds ratio that's useful. So the output is a prediction. So this is the big difference. Instead of the output being an odds ratio for you to interpret, the output is a prediction. It takes that one step further of, instead of a clinician interpreting the odds ratio, the machine learning program interprets that data and provides a prediction. And what we do next is that we take that prediction and we compare it to the actual outcome and see how far off the machine learning program is. And then we update the model using some clever calculus. And then it'll update in the direction to decrease the error. And we'll repeat this over and over again until this error between the prediction and the actual outcome is minimized. And this is what we call the training step of machine learning or optimization. So this is the big difference between the machine learning approach and the manual scoring system odds ratio analysis approach. Now, what we can do next is that after this model is optimized, we can take just this model, put it on a USB flash drive, bring a new patient in, and then use that new patient as the input. And then the output will be the new prediction for that patient. For instance, this model might predict the probability of group A strep. And you take a new patient in and you'll get that prediction for that new patient. Now, at this point, it's a little bit different way of looking at data. Feel free to ask in the chat or speak up if there are any questions. Take a 1-minute question break while I set up the program. All right. So if there are no questions, I'll move on. So next we're going to talk about different ways that we have to make sure how to do our due diligence to prepare our data for machine learning. It looks like a powerful tool, but it's not invincible. We have to make sure we prepare the data really well for it. So there's a lot of problems with data. So this is the data set I presented last time. It's a bunch of hockey players from a bunch of divisions. We have their oral temperature, age, whether they have exudates, lymphadenopathy, and then the outcome we're trying to measure is whether they're group A strep positive. So the problem with data is, especially when we're doing linear analysis, linear regression, odds ratio, p-value, is that data is often nonlinear, especially in biology. For instance, if we just compute an odds ratio based off, let's say, oral temperature, then we're saying that, well, it doesn't matter what your age is, your oral temperature will have the same odds, which we know is not true. People that are older have a more difficult time mounting immune response. So there's a difference in probabilities between age 5 to 50 and also from 50 to 53. It's nonlinear and it's also interdependent within each other. Another problem is that there's a lot of confounding variables that usually aren't captured. So for instance, what if people at different ages were interacting in different endemic regions? Then their baseline probabilities would be different. So another big problem with data is that sometimes our data is not detailed enough. And this happens a lot with surveys. Surveys are notorious for this. And it's not really the fault of the surveyors. It's because usually social metrics aren't the most exact. So something like this, whether they have tonsil exudates or not, just saying yes or no is classifying an entire spectrum of exudates into 2 classes. So we lose a lot of information in between. So for instance, the size of exudates might matter on whether they have group A strep or not, but this data set would not represent that. So the tip for your data set when you're preparing is try to have as much detailed data as possible. Continuous data is amazing. Machine learning loves continuous data. For instance, oral temperature or even age. It's much better than whether their lymph nodes are inflamed or not. And then sometimes a lot of studies present what I call tunnel vision conclusions, right? For instance, you look at the Atlantic. The Atlantic has a higher odds of having group-based strep than people from Pacific. So would you make the conclusion that the Atlantic is having strep problem? Well, you have to consider, did you take into account all of Atlantic patients? Did you control all the confounding variables? A lot of studies don't do this. And there's this one notorious paper that was out recently, which if we have time, we'll look at, that falls into this trap. Next is, like what I said before, machine learning loves continuous data and also loves numerical data. Categorical data is a little bit hard to deal with, binary data included, because you lose a lot of information. When it's just 0 and 1, there might be a lot of information in between. Sometimes when it's a clear-cut 0-1 digital signal, that's fine. But something like, for instance, if this oral temperature category was just febrile or afebrile, I'd say that's a pretty bad feature. We want as much detail in that feature as possible because machine learning is really good at sniffing out those details. So what we can do when we see categorical variables is that we can create dummy variables, which is a binarization of these variables. For instance, instead of saying what region they are and if they're in Atlantic or Pacific, we can give them a 1 if they're in the Atlantic, or 1 if they're in the Pacific, and 0 for the other regions. The problem is that now we're creating more features. So before we only had 5 features, now we have 6, which means the more features we have, the more data we need to properly capture all the confounders and properly capture the distribution of that data. And we'll see later on, there's always the question of how much data do I need? There's no clear answer, but the more features you have, the more data you want to add, which is why I don't really like these continuous categorical variables, because the more categories you split, the more data that you'll need. So a tip I always give is get lots and lots of data. So this example, we have n equals 5. You can't draw any conclusions with n equals 5. In classical analysis, a lot of people use Cochrane's formula, which usually I think for 95% confidence interval for normal distribution, you want 390 samples. That is usually still not enough for machine learning. And we'll see why. So get as much data as you can. And this is sometimes hard to justify because when you're giving a proposal for NSERC or CIHR, they sometimes ask for sample size calculation. So my tip is look at some sample machine learning papers. They'll all say we want as much data as we want. We want 10,000 samples, 20,000 samples. And there's no clear mathematical justification, but there are simulations that have been ran saying that 10,000 to 20,000 is a good number. And this question always comes up. How much data do I need? The best answer is still, I know it's a cop-out, but as much as you can get your hands on. Now, it's not definite, but there's a rule of thumb where it's 10 times number of features per outcome. This is really just for logistic regression. It's really 10 times the number of degrees of freedom, because if your model has many more variables, then you need a lot more samples. So this is okay rule of thumb. So let's say you have 10 variables, 10 features. This will say you want at least 100 samples. That will get you to an okay proof of concept stage, but you cannot claim that no one will trust you if you say that your model is able to capture and predict everyone in the world. So you'll need a lot more data to do that. So this is 2 examples of 2 studies. So if you want a publication that changes guidelines and is implemented high impact used in clinics, like the PCARN example we used last week for pediatric head trauma, then you want 5,000, 10,000 samples, because you want to claim generalizability, saying that our model doesn't just work for our specific case, it can work for your hospital as well. If you just want a proof of concept, especially when you're working with really complex data, this happens in video analysis, image analysis, where it's really complex analysis. You can get away with 200 to 300. I've seen publications with 100, but here you're really relying on the novelty of your method rather than saying your thing has really high immediate clinical impact. Now, this comes back to the point I said before. When you expand the dummy variables, you increase your data demand. So by doing this, I just increase the data need by, let's say 10, if I'm going by that rule of thumb. what we can do to increase the amount of data is a technique called data augmentation. This is when we change our data slightly so that it still retains the key features, but it is mathematically different. For instance, on an image analysis program, if we're trying to figure out if the image is a cat or dog, and we have this data point, this image, we can rotate it, we can translate it a bit, we can even flip it. So in this example, they've done this 9 times, and really the key features of cat is still there. A human can still recognize this is a cat, but mathematically, each one of these matrices has different numbers. So your machine learning algorithm won't just look at these ears in this location, right? It'll learn to recognize the texture of a fur, for instance. So data augmentation is a very useful tool that's used quite often, especially in image and video analysis, because it's quite easy to augment an image while retaining the key features. This is a bit harder to do if you have numerical data like lab values, right? If your sodium is, let's say, 120, and how do you augment that? You can't increase that to 130. You can't decrease it. You can't have it, because that makes no sense. You're changing the key feature of that data. So you'll need something like an image where it's a matrix of numbers that you can adjust a bit. There are also additional variables you can add. This is sort of in the realm of transfer learning, where we talked about last week, where you add some really important feature that has value into your model. So for instance, this is an ultrasound image of a trying to look for a gallstone, I think. And these researchers decide to add entropy as a variable. Now, entropy means how surprising data is as you go in a direction. So they say, well, stones are really surprising because you're suddenly really bright and then suddenly really dark. So this is a really useful feature to add to our data set. So this is something that a lot of electrical engineers love, which is to add a Fourier transform. Now, Fourier transform is one of the most useful tools for electrical engineers, for ECGs, for frequency analysis. It's when you convert some sort of periodic signal into its frequency components, because every periodic signal is composed of a sum of sines and cosines. So what engineers can do is that they can take your signal, take your data, and do a Fourier transform and use that output as data to feed forward into a machine learning algorithm. Now, this is not a entire exhaustive list of all the potential ways you can enhance your data set, but these are just some ideas to show you what's out there. Now, once you sort of prepare your data, it's always a good idea to perform what's called an exploratory data analysis. When you look at examples on the internet, a lot of people will do this as a first step. That's when they just look at descriptive statistics of the data to see if there's anything that really doesn't make sense. So for instance, if you have variables that have really low biological plausibility, you likely want to throw them out, right? So you might get some correlation, but you don't want to keep them because it makes no sense. For instance, this is an example where there's a really good correlation between the number of people who drowned by falling in a pool with the number of films that Nicolas Cage appears in, right? And this is an example of correlation not equal causation, which is notoriously used in social media. So some things you can do. For instance, you want to remove features that are low variance. Let's say the temperature of your patients, it's all at 38. Well, that's a useless variable, right? You want to also remove collinear features. These are features that are exactly the same. For instance, if you have height and BMI and weight as features in your model, well, BMI has a linear relationship to height and weight. So it's pretty much the same variable, right? It's going to add dimensionality to your model. It's going to increase your data demand. So you can remove it. A technique to do that is, for instance, the variance inflation factor. A lot of other techniques to do this, but this is the one that I use. So, and the goal is really to reduce the dimensionality of your data set so that you have enough samples for the number of features. A lot of other techniques to do this. Some people like to do a ANOVA analysis or a Pearson correlation and remove the low p-value features. Some machine learning techniques have this built in, like neural network or random forest. The way they optimize, they sort of decrease the weight of the irrelevant features, but some don't, like logistic regression. And my advice is to not rely on the built-in optimization of these models. So for instance, this is one example of something that someone's worked on in the past, where they try to look at, the odds ratios and p-values of different variables predicting depression. And they found that some were like had really high p-values and probably we didn't have enough data for, so they removed those features. Now this is afterwards. I know we said to look at the correlation ratios, but this don't conclude with the correlation ratios on predictivity, because I can force a correlation with anything, right? Here's a data set, and this is, you know, an underfitted poor correlation curve. This is a good fit. This is what we consider a robust fit, because this fits the trend of the data. But this is not the highest possible correlation. This is the highest possible correlation here, where we're hitting every single data point. And mathematically, we can do this easily. Just have a 500-degree polynomial, and we can fit every single data point in here. But when a new data point comes in, we won't be able to capture it because this is overfitted to our data set. And this is a really important key point. This is when we review papers, the number one reason why we're skeptical of some methods is overfitting, because some researchers, they train their model on their entire data set and they make it so complex that they have higher accuracy for their data set. But when new data comes in, they aren't able to handle it at all. This is overfitting. This is a very, very, very important point. Especially before common due diligence processes were standard. So before 2000, a lot of studies had overfitted models. They claim very, very high odds ratios, but their model does not work when you bring it to another hospital. Right? And number one reason why people do this, at least when I reviewed the papers, was because they built their model on their entire data set. This is bad, not good. Never, ever, ever build a prediction model on your entire data set. You have to leave a bit out of the model for it to predict afterwards, as if it's blinded. This comes in the topic of generalizability. Why do we want to do this? Because we want to generalize our model. We don't want our model just to work with our hospital's patients. We want to bring it to another hospital and have it work for those patients. Otherwise, our model is not very useful. And their main techniques to do this before we build the model and after we build the model. So before we build the model, we want to make sure our data is from a varied source. We want to have different ethnicities, ages, samples from different locations. And then we want to essentially introduce as much confounding variables as possible, because the more confounders we have, the tougher it is for a model to train. And if it survives that training and has high accuracy, that means it's able to handle confounding variables from a diverse population. Now, the way during model building, the way we do this and ensure generalizability is a technique called cross-validation. This is very, very important. If there's one thing I wish medical students take away from these sessions, it's this. When you're building a model and doing analysis, please consider cross-validation. This is what cross-validation is. For instance, this is five-fold cross-validation. You split your data set into 5. So let's say I have 100 samples. We'll split into bins of 20, right? We'll train on, say, 80% of the data. And the last 20%, we're going to hold it out until afterwards. So while we're training, the model is blinded to this test set, right? It's as if it's data from a different hospital that the model has not seen yet. And then afterwards, once it's done training, then the model will be tested on this data set, right? So this is sort of like testing the model on new data coming in. It really tests the generalizability of the model. And this is the accuracy that people should report. And then you can repeat this 5 times, hence the cross part of cross-validation with different 20% bin used as a test set. And then you can average the accuracies, right? And this is a bit of simplification, because within this training step, there's actually another split of the model building process having its own training and testing. But the point I'm making is that you always leave a holdout set to test your data, and then you can average the accuracies afterwards. So if a paper comes up with these metrics saying we perform 5-fold cross-validation or 10-fold cross-validation, and these are our average accuracies, then it'll be much more believable that they did their due diligence to make sure they're not overfitting. So the takeaways from this sort of data due diligence part is that people should always be critical of statistics. There's a lot of misleading correlations, odds ratios, and really you don't want to be misguided by that. Try to get as much data as possible and clean out the data. So remove data that's not biologically plausible, remove collinear data, change categorical variables to binary variables, and always cross-validate your model so you're not overfitting. Okay. So now we have a bit of time. We're going to talk a little bit about specifically to machine learning, supervised and unsupervised learning. But at this point, if anyone has any questions, feel free to type in the chat. Well, we'll take a 2-minute break.
Can you talk for a second again about that? I think you called it the sinusoidal augmentation.
Yeah. So it was the I think it was the Fourier transform. Oh, sorry, that was a bit. Oh, where was it? No, it was a bit after this. It was here, wasn't it? Yeah. Was it this one?
Yeah. So just explain to me again, sorry, what's going on here.
Yeah. So
I don't remember my sign trend.
Yeah, no worries. So this is a electrocardiogram where it's a periodic signal. In electrical engineering, there's a theory that any sort of periodic signal, it doesn't matter what it looks like, as long as it repeats, we can express it as a sum of sines and cosines. And each one of those sines and cosines is associated with the frequency coefficient. So for instance, for the human heart, we expect when we do the Fourier transform and we see the plot, we'll expect a spike at around 60 beats per minute or 70 beats per minute, 60 hertz or 70 hertz, right? So what this does is that it sort of simplifies the data. There's this sort of messy, wiggly signal, but when we look at the Fourier transform data, what we'll see is that we'll see a spike at the frequency at which the heart will beat at. So instead of taking this ECG, what some data scientists do, they transform the data so it's a little much more manageable. So that instead we have this data where say we'll have 60 hertz as the variable. And then that makes that data much more biologically relevant to whatever they're analyzing. So this is just a technique to transform data to make it more usable.
Yeah, I'm gonna have to puzzle on that one.
Yeah, no worries. There are lots of this is a bit it's something that's introduced to second and third year electrical engineers, and they use it a lot in signal analysis for medical signals. So it's not something that's immediately intuitive and understandable. So yeah, it's okay. It's an example that we brought in just to show some advanced techniques to transform data. Okay. Anyway. So next we're going to talk about something specific to machine learning. So in machine learning, there's two major categories. There's supervised learning and unsupervised learning. So supervised learning means we have labels for the outcomes which we want to predict. And unsupervised means we don't have labels. Why do I mean by labels? Say, for instance, we have this data set. We have our blood pressure, heart rate, and the outcome we want to predict is whether the patient has diabetes. This column, whether the patient we have diabetes, is called the label. It's the outcome, it's the ground truth, right? It's in supervised learning, it's there, and it's available for us to validate our model. In unsupervised learning, this is not available. We only have the variables which we think are relevant, but we don't have the outcome. So at first, this is a bit unintuitive. How do we make a model if there's nothing to compare it and validate it with? So with unsupervised learning, the goal is usually clustering, which we have different groups of data. Let's say these are different patients with heart rate and blood pressure combinations. And we want to create categories where they're separate, meaningfully separated. So here, this is a really obvious example where there are 3 obvious categories, and then a clustering algorithm would separate it into these 3 categories. Now, this is quite a difficult field of machine learning. We're not going to go in depth into it because in medicine, most of the work being done, at least especially for the medical student level, is in supervised learning. You have the outcome and you want to build a model that predicts the outcome. So there's one technique that we can do in both, which is called dimensionality reduction. Earlier, I talked about how difficult it is when we don't have enough samples. So one thing we can do is reduce dimensions by transforming the data. So here, instead of using blood pressure and heart rate, we can do a metric, say heart rate squared minus systolic blood pressure, right? This might not necessarily be entirely accurate, but there are techniques, know that there are techniques to do this. So if you have way too much data and you're working on a project, you can potentially explore if anyone has done dimensionality reduction on your data set. Now, the topic we're going to talk about today is logistic regression. So linear regression is when we, for instance, try to draw a straight line through our variables and model that trend with a straight line, right? And this is the linear regression equation. Logistic regression, on the other hand, is when we have two classes. It's sort of an extension of linear regression, except our curve is not linear anymore. But our curve is used so that we're splitting our data into two. So we're using this for classification, right? Mainly so our outcome should be binary. Our outcome should be if the patient had diabetes or not what their A1C level is, for instance. So this slide was made by Prash, and he loves Lord of the Rings memes. So this is an example of logistic regression. So I know the word regression is used a lot in statistics and machine learning, and it's a bit overused, but really logistic regression is a classification technique. You're regressing to a curve, but for the purpose of classification. So here, for instance, we have our data set separated by tumor size, and then the class is on the y-axis. So they're either benign or malignant. Logistic regression is when we try to draw a logistic curve, which looks like this, to separate the data set. And this sort of looks like, a line drawn through the middle vertically to separate two classes, except a vertical line is not mathematically friendly, because the vertical line, the derivative is infinity. We can't work with it. So instead, we have this logistic curve, which is very mathematically friendly. And this is the logistic equation. You don't have to worry about it. Just know this W and B, these are the weights. So this, when a machine learning model trains, this is what it'll update. It'll update these weights and the B parameter for every variable, so that this curve fits the data and is able to separate data as best as possible. So again, these weights is what changes during machine learning optimization. For instance, this is an example of the logistic regression curve that's moving at different when your thresholds are different, it'll move slightly and it'll optimize to classify these two classes. And this, I think there's an animation coming up there. So again, the key machine learning process model, we start the model and then we adjust the weights until we have the best accuracy. And the different optimization techniques, you don't have to worry about what they're called. Just know that they're in calculus. We can use some clever calculus to optimize them. So instead of a clinician manually changing scoring values to have the highest accuracy, we can use calculus so that we change all the parameters at once to ensure that the combination results in the highest accuracy. This is an animation of a logistic regression in linear regression in progress. So you can see that this curve is constantly being updated so that some sort of loss function is being computed and the accuracy, it's being adjusted until the accuracy is maximized. And this is logistic regression. So there are two classes, and this is a logistic regression curve, and this is the machine learning program running. It keeps running until this curve, the weight and the B parameter of this curve is at an optimum, so that you can separate these classes as best as possible. Okay, so this is one of the most common statistical analysis methods used, but not for machine learning. It's traditionally used to generate odds ratios, because you can convert this weight and this B parameter into an odds ratio, but it can be used for classification. And we'll see an example of that in our programming example. So before we move to the programming section, are there any other questions? I'm going to share the program. Okay. So while I set this up, I'm going to share the link to everyone. And this will all be shared on the website and on Slack channel as well. Sure. So I'll share it in the chat. So again, to get it set up, click the link. The first thing you have to do is go File and then save a copy to your drive so that you can edit it. So I'll give about two minutes for everyone to set up, and then we'll start running through this program. Sorry, one moment. Someone just messaged me about the course. Okay, so this is so all credit of this goes to Prash. He set up this amazing program to demonstrate some machine learning techniques that we looked at just now, specifically logistic regression. There's some dimensionality reduction portions here, which I'll leave in here and I'll share with everyone, but I don't think we have time for that. So we'll mainly go through the logistic regression part because I think that's quite high yield for a lot of medical student projects. So this is first step we have to do. Again, to run this, click on a cell and then either click the play button or control enter to run the code in that cell. So what we have to do first is we have to load in all these libraries. And these are standard libraries, sklearn, pandas, NumPy, standard libraries for us to manipulate data. So I'm going to click the cell, control enter, right? And you don't see an error, that means it's successfully loaded. So this first part, Prash provided an example of unsupervised learning, where we're trying to cluster the data and then also perform something called principal component analysis to see what's really the important component of this data set. If we have time, we'll go through this. I don't think we'll have time, but I'm going to scroll down to the logistic regression part. Okay, so we'll go down to the supervised learning classification with logistic regression. But make sure you run that very first cell at the very top because that has the libraries that we need. So we're going to start with the exact same data set we used last time, the breast cancer data set. So if you remember this data set, it's a bunch of imaging features like the size, whether the perimeter of the tumor, and I think it's around 30 of these features. And then the outcome is whether the tumor is malignant or benign. And we want to predict with those features whether the tumor is malignant or benign. So this is a labeled supervised learning example. So we can run this for this first segment of code. So this is just loading in the data. This is just manual labor. So I didn't leave this blank for everyone to put in because this is something where if I was doing this project, I'll look up how to initiate a data frame, right? So it's not something that's very insightful into data analysis. So we can run the cell, control enter, and we see, okay, there's no error, but it's not really descriptive. So what we can do is that in these cells, when we just type a variable name, it'll display that variable. So I want to display the data frame that the data is stored. So the data frame is labeled, it's called df, right? So I'm gonna say df, control enter, and it should spit out the data frame. Okay, so this is what our data is. We have the radius, texture, perimeter, area, smoothness, concavity, symmetry, right? And then we should have the outcome at the very end. So the label, right? 0 is benign, 1 is malignant. And this is your data set should be organized similarly. So with your variables and then some sort of outcome column that's labeled. So now we want to be able to classify this. We want to use logistic regression to see if we can use these variables to predict if it's malignant or benign. Remember last time when we did a correlation ratio, we had about maybe 0.3, 0.35 was the best correlation. So if we just use linear correlation, we're not going to do very well. So this is not code. This is part of the text. It's just some instructions showing you what the logistic regression curve looks like, what the equation looks like, right? So now what we want to do is that we want to put this into a logistic regression model object in Python. So the way we do this, so first we have to split the data set into training and testing, and sklearn has a function for us to do this called train test split. So this is just manipulating data. So I didn't exclude this, but first thing what we want to do is after we split it, we want to visualize what the features look like in comparison to the label. So what we can do is, we can plot this. So after the trained and test splits are created, we want to create a figure. So the way we do this, we use plot. We use the plot library, plot.figure. This starts a figure. Right? I want to create a scatter plot, plot.scatter. We want to look at, say, the first feature. So here we extract the first feature from the data set. Right? And then on the y-axis, we want to have the outcome. Right? So, and then let's label the axes, so it makes it easier for us to label, let's say, first feature. Okay, I'll label the y-axis as well. Label class. Okay, so now let's run this. I think there will be error, but I know why. So I'm gonna run this and see if our plot appears. So, okay, well, our plot did appear. So this is what the first feature looks at, the first feature value. And if we look at what's our first feature, mean radius, right? So mean radius compared to the class. Right? So there's some, if we draw a straight line, you know, if we do a Pearson correlation ratio or something, or odds ratio, if we do a straight line, yeah, it's not going to do that well. But we see there is some sort of trend that we can extrapolate, perhaps with logistic regression. Okay, so let's get the logistic regression curve. So the way we do this is I'm going to call the logistic regression curve log reg. Function called logistic regression. And then within this function, we have what's called some of them are called hyperparameters. So these are parameters within the model that aren't automatically optimized. So you have to manually input them. One of them is the number of iterations. So max iterations, let's go 5,000 iterations, right? And then just so we all get the same results, you can specify a random seed. This sort of tells you how things are randomly initiated. So I'm going to say my random state as 1. Okay. So this just creates the model. So now I want to fit it to our data. So I have to say log reg equal dot fit. Do it on one feature, X train, one feature, Y train. So this fits a logistic regression model on just the first column. Okay, and then let's see, and we want to visualize it afterwards. So I'm going to create another plot again. And it's another scatter plot. So scatter now, X train one feature, Y train, which is our outcome. But now I want to add in the logistic regression curve. So, well, how do I do that? Well, I know logistic regression curves equations like this, and the weights are going to be whatever is optimized from this function, right? So I have to create a vector for the X coordinates and a vector for the Y coordinates for this. So we do this, let's call it sigmoid function X. We could create a linear spacing from -2 to 4, 500 points. Okay. And then we'll shape it to the dimensions of our plot. So this part's a bit extra. You already created a logistic regression model. This is just some extraneous stuff to visualize it really nicely. So if this doesn't come right away, don't worry about it. So this is a logistic regression equation. It's the exponential of that X value multiplied by the coefficients in that logistic regression, right? And then plus the B, which is the B parameter, which is the intercept. Okay, then let's plot this on the same plot. Next, make color red. All the programming languages are American, so all spelling is American. Okay, so let's run this and see if I made any typos. Okay, made a typo here. X train is X train one feature. Reg. So here. So this is our logistic regression, right? Our logistic regression trainer trains it and it's able to fit a curve like this. So it's not perfect, it's okay, but you're going to miss some patients doing this. So you don't want to use this clinically. And what's the accuracy? Well, the test accuracy is about 86%, which you know, it might be really, really good, better than whatever standard practice it is. But we can improve it better. Remember, we're doing this based off only one variable. What if we do logistic regression on all the variables, right? Then we'll have a much more meaningful model. So that's exactly what we'll do right after. So we want to train the classifier on all the features, right? So now we will be doing the exact same thing, except this time I'm not gonna visualize it because typing those plots is a bit tedious. So let's fit, instead of just that one feature, we're gonna fit all the features. So X train, capital X, Y train. Okay, this is fitting the logistic regression model, and let's print all the metrics. So let's say train error, reg score X train. This is within the logistic regression model in Python. There are different, these called methods. Where you put a period, that means within this library, there's this function called score, which will give you automatically the score of that model. So this is where we print the training and testing error. Remember, the one that you really want to pay attention to in papers is the test error, because the training error can be overfitted, but testing error, if they do a train test split, it should be like testing on new data. Right? Okay, let's see, did I typo again? So now when we're doing all the features, we notice that the train error, the train accuracy is 0.99 and the test accuracy is 0.97, right? This is expected, right? Our training accuracy is much higher than our testing accuracy. And really that's what should happen in real life. Your testing accuracy should always be a bit lower because your model hasn't seen that data. You always do worse on new data theoretically. So it's doing really well when we look at all the features. So if this was 20 years ago and I gave you guys this code, you'd be able to publish something. Now what we can also do, just be in line with classical biostats, people really like the odds ratios for logistic regression. So because logistic regression was traditionally used as sort of an informational technique to look at odds ratios, we can extract the odds of each variable. So the odds of each variable is, when you look at the logistic regression equation, it puts all the variables in this exponential and it has this weight function. So the odds is actually the exponent of that weight, right? To get that, you have to take the logarithm of both sides and do some mathematical gymnastics. But if you look on Wikipedia or a textbook, there's a way to get the odds ratios out. Luckily in Python, they already provided that in library. So all we have to do is say logreg dot coefficient. And then we also look at the intercept variable, intercept. Okay. So these are the model coefficients. So again, I said you have to take the exponent of this to get the actual odds ratio. So for instance, let's say print negative 0. Let's look at what the odds ratio is for that first value. I have to do, what was the, so let's say mean radius, okay? So, sorry, I have to go to the NumPy library to do this. Okay, so these are the coefficients, which is that W parameter, but it's not odds ratio select. To get the odds ratio, which if you do SPSS or Sigma Stat or some other stats package, they do it automatically for you. The odds ratio for that first variable is 0.63, right? So you can see there's some association associated with it. And when you do a publication, you should report those odds ratios if you're doing logistic regression. The main takeaway is we're not doing a biostats sort of inferential analysis. We're doing a predictive analysis. So what's really important for us is this test and train error. So to have a train accuracy of 0.99 and a test accuracy of 0.98, that's amazing. So it shows to you how good logistic regression is. Remember, our correlation analysis only had correlation ratios of 0.34 or something, right? So imagine taking those correlation ratios, doing some manual scoring system. You're not going to get 98% accuracy, but with machine learning, you could. Now, there's some further steps you want to do if you want to make this publication ready. You still have to do cross-validation, right? We just did one split. We didn't cross-validate it multiple times. So you have to do cross-validation. You have to report all the odds ratios and then talk about the biological plausibility of each ratio, right? Because something that clinicians hate about machine learning is that it's a lot of black boxing, right? You give them the logistic regression equation, say, hey, this is how to predict patients whether they're malignant or benign. They're not going to be able to interpret it. So you have to look at each of these variables. Say mean radius is really predictive. Well, what does that mean? The radius of the tumor it's correlated with how much the tumor is growing, therefore it's predictive. But we have to do it in this mathematical logistic way to make it predictive. So that's a good argument. So we'll see in the next few weeks a lot of different other machine learning methods. Logistic regression is one of the most basic ones. It's not used that much. There are other methods that are much more popular for more complex problems, which we'll explore, and we'll show some programming examples, and then we'll show you when to use those and when not to use those. But for now, this is logistic regression. This is how you program it. You can take this code and use it on your own projects if you want. And it's really great to see that even with this basic model, machine learning does really, really well. Okay. At this point, that's it with our programming examples. Feel free to ask if you have any questions. I'll be around for another 5 to 10 minutes. And I'll also stop. Yeah. Let me stop the recording.